Hello everyone, welcome back to the another session in design and analysis of algorithms. Today we'll be going to talk about convex hull. So this topic you can find it out in unit 2 topic 8, the last topic of second unit. Now this video will helps you out to understand what is convex hull problem and how to solve this convex hull problem. So basically we'll solve this problem using brute force approach. We'll find all the possible solutions to find the one optimum solution. Now we'll see what is convex hull. A convex hull is an important structure in the geometry that can be used in the construction of many other geometric structures. So the convex hull of a set S of points in the plane is defined to be the smallest convex polygon containing all the points of S. If I consider these are S points, then my convex polygon should contain all these points. Now it is called as a convex polygon. If you take the other example also, now it is also called as convex polygon. So convex polygon is what? It should contain all the points has to be contained in the set S. Now, can I call all the polygons as convex polygon? No. There is a constraint to call some polygon is convex polygon. That is, a polygon is defined to be convex if and only if for any 2 points P1 and P2 inside the polygon. That means if I take some set of S points, now I am joining all these S points. Now look at this. If I draw a line in between of these 2 points, now this line segment is inside of polygon and this inside also it is fully contained. If you take the other example of points, now if I draw any line from P1 to P2, it is inside of the polygon, and inside of the polygon also it should be fully. If I draw P1 is here, P2 is here, if I draw a line segment from P1 vertex to P2 vertex, now what happens? Only some portion of the line segment was covered in inside, other portion is covered at outside. So it is not called as convex polygon. Only it is called as convex polygon. By mathematical definition, if you join any 2 points, it should lie completely within the polygon. So as far as the definition, first is called as convex, second is not convex, because when I join these 2 points, only some portion is inside, and so it is not convex polygon. So now you have to focus on this. Now you have to consider one convex hull and find out all possible convex hulls and find out the shortest one in order to call it as a convex hull. Now we will be going to take some example and we'll solve it. Now look at this one. The vertex of the convex hull of a set of S points form a subset of S. So all the points are inside of the polygon. So when all the points are inside of the polygon, when you are covering fully, then that is of convex polygon. Now there are 2 variants of the convex hull problem, which is we have to obtain the vertex of the convex hull. Now here each vertex is called as extreme point. After that we'll obtain the vertex in such a way by specifying some order, which is example clockwise, anti-clockwise. So we'll go with an order. We'll obtain the vertex in an order. Now, there is a simple algorithm for obtaining the extreme points of a given set S of points in the plane. That algorithm is to check whether a particular point P belongs to S is extreme. Look at each possible triplet of points and see whether P lies in the triangle formed by these 3 points. That means something like this. If we lie in any such triangle, it is not extreme, otherwise it is. Testing whether P lies in a given triangle can be done big O of 1 time. Since there are big O of n square possible triangles, it takes the same time, which is theta of n square, to determine whether a given point is an extreme point or not. Since there are endpoints, this algorithm runs in total of big O n square. So this is what we are explaining for this example, what we were taken. So for this example. Now we'll see about some example. Now look at this example. These are what the S points. Now as far as algorithm is concerned, the algorithm is what? Graham scan. Graham scan. So actually this convex hull, using divide and conquer, we can solve both the versions of convex hull problem with theta of n log n time. We developed 3 algorithms for the convex hull. The first has a worst case time of theta of n square, whereas its average time is what? Theta of n log n. This algorithm has a divide and conquer structure similar to that of quicksort. And the second has a worst case time complexity. So quicksort, you can see in the previous videos how we were used divide and conquer to find out theta of n log n. And the second case is what? Theta of n log n, and it is not based on divide and conquer. The third algorithm is based on divide and conquer and has a time complexity of theta of n log n in the worst case. Now we'll see some geometric primitives which will help us to understand how to join the line segments to cover all the points and to be called as a convex. Now let A be an n by n matrix whose elements are Aij 1 less than or equal to I and j less than or equal to n. The ith j minor of A, denoted as Aij, is defined to be the submatrix of A obtained by deleting the ith row and jth column. That is, the determinant of A denoted det of A is given by A11, where it is n equals to 1. When n value is greater than 1, we have to calculate for what? A11 det of A11 minus A12 det of A12 plus dash dash minus 1 of power n minus 1 det of A of in. So if you have only one element, then that means of 1 by 1, you will have obviously one element, that the element will be your det. If you have n greater than 1, we use this formula to calculate the det of the matrix. Now consider the directed line segment from P1 to P2. From some point P1 is equal to x1 comma y1 and P2 is equal to x2 comma y2. If I have a other vertex which is Q, now it is x3 comma y3. Now assume these 3 are the points. That's what vertex. We used to say these are vertex, but we are representing vertex as extreme points. Now Q is, I'm considering, is another point. We say Q is the left to the of P1 P2. If the angle P1 P2 Q is a left, that means right turn. An angle is said to be left, that is right turn, if it is less than or equal to, greater than or equal to 180 degrees. Now you can check whether Q is to the left or right of P1 comma P2 by evaluating the determinant of the following matrix. Now the matrix will be x1, x2, x3, y1 comma y2 comma y3, 1 1. So now we will be going to find out the det for this matrix. If this determinant, if this det is positive, then Q is to the left side of P1 comma P2. If this determinant is 0, now I'll write in neatly. as it is important, we'll take the cases once again. Now what I am telling is, when I have 3 points, when I have these 3 points, once after you find out the determinant of this matrix, if this determinant is positive, then Q is to the left of P1 comma P2. If it is 0, that means what? The 3 points are collinear. This test can be used, for example, to check whether a given point P is within the triangle formed by 3 points, say P1 comma P2 and P3, in clockwise order. That means your Q is here. The point P within the triangle if and only if P is to the right of the line segment. That means P1 comma P2, P2 comma P3 and P3 comma P1. Also, for any 3 points x1 comma y1, x2 comma y2 and x3 comma y3, the signed area formed by the corresponding triangle is given by 1/2 of the above determinant. Let P1 comma P2 up to Pn be the vertices of the convex polygon Q in clockwise order. That means this order. Now, let P be any other point. It is desired to check whether P lies in the interior of Q or outside. So for this, what we'll do is, we'll consider some H or horizontal line where it extends from minus infinity to positive infinity and goes through P. There are two possibilities. H doesn't intersect in any of the edge of Q, or H intersects some of the edge of the Q, or if it is the case, if the first case is true, that the first case is what? H doesn't intersect any of the edge of the Q, then P is outside of the Q. If it is not intersect, then P is outside of the Q. If it is intersect, then it is inside of the Q, correct? Now, we'll take some example and to find out which vertex, which extreme points I have to consider inside and which are not. Now we'll take this example and we'll move. I'm taking this example by using the algorithm of Graham-Scan. Algorithm is Graham-Scan, which tries to find out the point which lies inside of the polygon. Now let us take this one. So I'm taking this extreme point. For this extreme point, your y value is minimum, or it can be y is lowest value. So we will be, in order to find the angle and sort them accordingly, that means suppose this, I am assuming it is a P. The angle which makes from P to Q should be is less than from Q to R. The angle which makes from P is less than the angle which makes from R. So here we will be going to solve this thing by calculating the slope of your extreme points. That is, if I calculate slope of these 2 points P comma Q, the slope will be Q into Y minus P into Y by Q into X minus P into X. Whereas X comma Y are the corresponding X comma Y of the point. Similarly, Q and R is what? R into Y minus Q into Y, R into X minus Q into X. All we need to do just to compare these two lines. Now, if you do a cross multiplication of this, then that will be what? R into X minus Q into X. This Q into Y minus P into Y is equal to Q into X minus P into X, R into Y minus Q into Y. Now, by bringing RHS to here, this value will be R into X minus Q into X, Q into Y minus P into Y, minus q into x minus p into x, r into y minus q into y. If the value of this is 0, that means the 3 points are collinear as those were in same slope. If it is greater than 0, the points of P, Q, R will be making a clockwise order or clockwise angle P, Q, R. If it is greater than 0, the 3 points are moving into anti-clockwise P, Q, R points. As we saw in the previous figure, we always want an anti-clockwise angle, so we want to sort them in an increasing order. Now we will see choosing the points that, so I am just assuming these points x1, x2 and x3 and so on, x4, x5 something. So I am starting the extreme point from this x1. So now I am joining x1 point to x2. So that's what I'm maintaining a stack, always to keep the first 2 points into the stack, whether those are can be have line segment or not. Now x1, x2 are in the stack. So now let's see, x1 to x2 I'm just going in a correct direction, the way how I have to go, correct? So I'm just drawing a line segment over here. Now look at this, if I join x2 to x3 line, now let's take the next point, which is x3. Extreme point is x3. Now if I take this thing, now I have to turn left side to join this x4, correct? So now for that is the reason I am just ignoring this x3 from the stack. That means my direction from x2 to x4 will get moved, whereas x3 vertex or x3 extreme point will be inside of the polygon. So I am not joining this x3 to x2 to or something x4. I am directly taking x2 to x4 such that x4 should be in the stack. Now, so what elements were available in the stack? x1, x2, x4, saying that these are the line segments what I have from x1 to x2 and from x2 to x4. After this, again assume it is your x5. Now I am just turning right to join the x5. So once after, again I have to turn left to join the x6. If I take this version, then I told you in some order we have to obtain all the vertex and which is anti-clockwise. So when I'm moving it again, I have to turn right to this to join this vertex. So I'm ignoring again x6. Hence x5, x6, x6 will not be comes under the joint line segment. So x5 to x6 I am considering. So after this I am just moving into x7. That means I have to put in the stack after x1, x2, x4, then x5, but x6 is not included into this. x7 you can, x8, x9. Now look at this, I have not included x3 and x4, correct? So what I did, I have taken all the elements or I have obtained all the vertex to join all the extreme points in some order. The order is anti-clockwise order I have taken. Now we will maintain a stack, and this stack is consisting of what? The point what I have joined. x1 to x2 I found a line segment, and x3 I have deleted because I have to turn to the right opposite side of the going side. x4 is okay, x5, x7 and x8 and x9. So these are what the vertex or the extreme points through which we will be making it is a convex. So the final solution of this problem is what? x1 comma x2 comma x4 x5 x7 x8 x9. Now it is called as a convex because though you are not joining x3 and x6, those two are also available inside of the polygon. So this is what the solution of this problem. Now we'll calculate the complexity of the problem. The complexity is what? What we did first of all, first we will take the first point, which is y minimum coordinate, right? So when I take all the points in such a way, the points are n. Finally, the complexity is what? Theta of n or big O of n. So after that, you chosen the point what you are considering into it, you have to sort it. Sorting the points. We are sorting the points, and the complexity to sort the points is what? Theta of n log n. Now, each point once processed, then it is of theta of n. So, finally, the time complexity is what? Theta of n plus theta of n log n plus theta of n. So, finally, the complexity is what? Theta of n log n. So, this is the final complexity of convex hull using Graham-Scan algorithm. So, next video we will be going to talk about what is Graham-Scan algorithm. Thank you all.